Okay, just to continue with our class one more time. Last time we have seen the equation of orbital velocity. It was VO is equal to root over gr squared by r plus h. Then finally we derive the last equation v is equal to root over gr. We have derived these things. So today we will find the time period of the satellite. So we can write here to find the time period of satellite here. Looking at the figure again, this is the orbit of the satellite. This is the earth with radius r, height of the satellite b, h here. And here is the satellite. When it moves, it has orbital velocity VO with a mass of m here. It has to go along this circular orbit here. Then the total time taken to complete one full cycle. Let us see, what is that? If t is equal to time period means the time taken by the satellite to make one full cycle around the earth here. Say this is the starting point, we'll come back again, so there is a time taken, so that time is known as time period. So from the equation v is equal to length by time. Time will be length divided by v. So I'm going to use this one. So t is going to be equal to length. Length means the whole distance traveled by the satellite. So this is the starting point. Come back again to this point again. So the whole length of the circle should be twice pi r radius, but in our case the radius is r plus h here. So this whole length will be twice pi r plus h divided by v for the orbital velocity. So you can write down this vo here. So this is equal to twice pi again r plus h. Then you can write this vo. You can write as g r squared divided by r plus h whole power 1 by 2. You can write like this. So time period is going to be equal to, if you open the bracket separately, you can write like this: gr square power 1 by 2 whole divided by r plus h power 1 by 2. You can write it separately. Then this is equal to, this will multiply together here. Once it multiply, you can write twice pi. If this is multiplied, power is 1 here, so this will multiply here, so it becomes r plus h 1 plus 1 by 2. This and this will be added up here, divided by this term again. This is g r square whole power 1 by 2. This is equal to twice pi r plus h, this will be 3 by 2 whole divided by g r square whole power 1 by 2. Now you can write like this again: twice pi this r plus h you can write as half into 3 divided by z r square and power is what? Half again. So this is equal to, still writing twice pi. Then if you combine these two, you can take it as common here. The power is 1 by 2, 1 by 2 is common here. So you can write as r plus h. Let's use one more bracket. R plus h divided by, you can remove this one, it's okay. R plus h divided by z r square whole power 1 by 2, and this cube will be multiplying here inside here like this. So you can use a third bracket if you like this. I repeat again twice by writing here. This r plus h and this one having the same power here. So this r plus h I keep here, and this 3 is multiply here, and this half is taken as common here for both of them. Okay. Can you go to the next? So let us see how do we factorize it further. So now your t becomes equal to r plus h cube divided by z r square again. This is 1 by 2. Let me just rewrite again. If you try opening the bracket, you'll get the same equation. Twice pi. When you open the bracket, this will multiply. 3 power should be 3 into 1 by 2. Again, this is 1. Z r square. You'll get the same equation. So now, let us try to remove this square root. To remove the square root, let us multiply or just transfer this here. Just do squaring on both sides. T square is equal to, if we do squaring on both sides, 4 pi square will come, and this will be disappearing now. So we can write r plus h cube divided by z r square like this. Then doing cross multiplication, you will get r plus h cube 4 pi square. This is equal to, this will multiply t square z r square. Then r plus h cube, this is equal to t square z r square divided by, I write this one 4 pi square again. Okay. Then this cube I'll transfer on the other side. So it becomes r plus h only is equal to cube root of the right hand side, t square z r square divided by 4 pi square, and cube root of this you can write as power 1 by 3. So finally you can get the height here. So to get the height, you can write h is equal to t square z r square by 4 pi square and whole power 1 by 3 here. Then this r will be transferred. So this equation is used to find the height of a satellite. And you can also find the time period also. Time period, you can get it from here directly. This is already time period. You have got here. This is the time period of the satellite. And this one is used to find the height of satellite. These two are very important formulas. After we find the time period and the height of the satellite, we can see for this geosynchronous satellite that is included in the syllabus. So let us write that. This is all about geostationary, or you can call it as geosynchronous. So you can write here geosynchronous satellite. Geosynchronous, in this case, what happens is the satellite will move together with Earth here. Suppose this is Earth, this is the orbit of the satellite, and I select a point on the Earth, let us say A, and here is the satellite. So, whenever Earth rotates above the axis, satellite also will rotate in the same sense. Say, this is the satellite, this is the point I am having here. So whenever they move, they will be moving all the time together, all the time together here also. So if the satellite is supposed to be here, for example, then the point A will be shifting here again, like this. All the time they will be moving together. So such type of satellite is known as geosynchronous satellite. So to become a geosynchronous satellite, there are some requirements. The first requirement is satellite needs to move together in the same sense. That is from west to east with Earth together. And the second point is time period of the satellite should be exactly equal to time period of the Earth here. For Earth, it takes 24 hours to complete one rotation about the axis. That is 1 day. Similarly, time period of the satellite should be also exactly equal to 24 hours. So if the time period of the satellite and the Earth, if these two time periods are the same, then satellite will move together with Earth here. Then this type of satellite will be called as geosynchronous satellite. So you can estimate the height of a geosynchronous satellite. So what we do is, in this equation, if you put time period of the satellite as 24 hours, means changing into second, you can write 24 into what? 60 into, it's already changed now. 24 is already changed in terms of what? This hours, hour into minute, minute into second. So this one, and putting the value of z as 9.9 meter per second square. Radius of the Earth is 6400 kilometer, which is equal to 6400 into 10 power 1 kilometer means 3 meter. So when you put all these values here and when you factorize it, you will get an approximate value of about 36000 kilometer here. Though I am not showing you how to factorize it, you can remember this value directly. You may not be required to calculate everything here, but you know how to put in the formulas. You have to understand that, and you have to memorize the formula. And these values are to be used here, and after factorization, this will give you about 36,000 kilometer here. So this will be the height of the geosynchronous satellite. It means to be called as a geosynchronous satellite, the satellite must be at a height of 36,000 kilometers above the surface of Earth. So then the satellite will be called as geosynchronous satellite here. Okay, this is the brief introduction. The notes are there. You read the notes one more time. So the last derivation for this unit gravitation is to find the energy of a satellite. Let us do that right now. So write the heading. To find total energy of a satellite. Let's see again, how do we do? Total energy of satellite, let us say E here, this will be simply equal to sum of kinetic energy and potential energy. So first you need to know kinetic energy, then you need to know potential energy again. Let us do like this. So this is the orbit, for example. This is the satellite, the Earth here, with the radius of r, and the height of the satellite is h here. The satellite is supposed to move here, like this. Last time I told you that if m is the mass of the satellite and m be the mass of the Earth, there is a gravitational force. So the gravitational force should be g mm by r plus h square, equation number 1. And there was also a centripetal force, because satellite need to move with orbital velocity. Centripetal force was directed towards the center, and the centripetal force was equal to mvo square by radius. Radius of the orbit is what? R plus h here. So call equation number 2. Okay, let me get it from here. So from 1 and 2, if you do direct comparison, you can write mvo square by r plus h. This is equal to gmm by r plus h square here. So just cancel these two. Give it like this. mvo square should be equal to gmm divided by r plus h is left here. So you have this mvo square. So if you multiply by half on both sides, so multiply by 1 by 2 on both sides, okay. So if you multiply by 1 by 2 on both sides, you get this. Half of mvo square is equal to gmm by 2 times of r plus h here. So this is your kinetic energy, half mv square. So directly you can write kinetic energy is equal to gmm by 2 times of r plus h. This is the equation of kinetic energy. Then we have to see for potential energy again. Potential energy equation is exactly equal to gravitational potential energy that we have derived last time. So if you remember that the gravitational potential energy U was equal to minus gmm divided by the whole height. Actually the equation was U is equal to minus gmm by r, but in our case the whole length becomes r plus h here. So you can write r plus h. This is your equation 1, equation 2 here. This is the potential energy of the satellite here. So now put back in the equation of total energy. Therefore, total energy of the satellite, let us see what we get. Total energy of the satellite now, it should be equal to, kinetic energy is there, gmm divided by 2 times of r plus h, and plus minus will become minus gmm by r plus h second here. So you can take this gmm by r plus h common. If you take it common, you have 1 by 2 minus 1. 1 by 2 minus 1 is left. This is equal to minus 1 by 2. So you can write gmm by r plus h. This is equal to what? Minus 1 by 2. So now you have minus gmm by r plus h here. So this is going to be the total energy of the satellite. Total energy of the satellite is like this. Now, this total energy of the satellite is negative simply because the satellite and the Earth, they attract each other here. The negative sign shows that. So write down. The negative sign shows that Earth and satellite forms a bound system. Bound system means both satellite and the Earth are binded together by gravitational force of attraction. I repeat again. The negative sign indicates that there is attractive force between the satellite and the Earth. All right. So now you can see as the energy is negative, when the satellite is moving away farther and farther, the gravitational or simply total energy of the satellite will go increasing. Because if there is no negative sign, if this is increasing, this should be decreasing. R plus I is increasing means I is increasing means you keep on increasing the height here, energy should be decreasing. But there is negative sign. Negative sign means whenever you increase this quantity, energy also increases here. So the meaning is when the satellite is moving farther away from Earth, that simply means that it will increase. That's why total energy of the satellite will increase. So total energy of satellite increases with height. It means when height increases, total energy of the satellite will increase. But kinetic energy of the satellite will go on decreasing simply because when you keep satellite at a farther place, the satellite orbital velocity will be decreasing. Last time I told you that. And if satellite is closer, orbital velocity is very fast. If it is farther away, orbital velocity decreases. It means if VO decreases, kinetic energy is equal to half of mVO square. If VO decreases, kinetic energy decreases here. So it means when you consider the satellite at a far place, the kinetic energy simply decreases here. But total energy will increase, but kinetic energy will be decreasing here. That's why we can plot a graph here. So this is the distance. This is the negative axis here. This is the positive axis. So now from this equation of total energy, just now I told you that when the distance increases, energy decreases. That's why the shape of the total energy of the graph should be like this. This graph should be the energy. Why? Because when you increase the distance, increasing the distance means from negative it comes to the origin here. Suppose this point and this point, choose now. If you choose this point here and choose this point here, distance increasing means the energy is coming towards the origin. It means by energy is increasing here. When you move like this is the increase, isn't that? And what about kinetic energy? When kinetic energy means that when distance increases like this, when distance increases, I told you the kinetic energy decreases. That's why when r distance increases, kinetic energy should be decreasing like that. So this is your kinetic energy graph. This is the total energy graph here. So it looks like this. This is the distance. Your kinetic energy looks like this. Total energy looks like this here. This is the kinetic energy. This is the total energy here. And this is positive axis. This is the negative axis. This is the origin here. This is the graph. So with this, I have already completed the theory of your gravitation. That is one full unit. We have finished. So I'll be adding up some question answer in the next class, and with that, this unit will be done here. Okay then, see you in the next class again.